beginning of this talk, and I'm going to use this time, and I propose that we thank Christina Kuperberg for organizing this conference. I hope believe me, she really did all the work. And I hope that this is not hubris, and I hope that this Parker Hall will last for the next hour. Okay, well, it's my pleasure to introduce the next speaker, Janusz Prajs from University of California in Sacramento. The continuum theory session was dedicated to Janusz Prajs, and we heard a lot of nice things about him. So let me say only that he is by far the foremost expert on homogeneous continua, and he will speak well about open problems in the study of homogeneous continua.
First, I would like to thank everybody for being patient to wait until the very last meeting. I thought that I will have maybe 10, maybe 20 participants at the audience, but it turns out much better. A little comment. In California, there is the difference between University of California and California State University. I am from California State University.
My apology to you and to the state of California.
Outside of California, it's very easy to make such an error. I don't know if it is visible well, or perhaps we should dim lights a little bit. How is it? It's fine. Yeah. Okay. So this talk is very personal. I do not claim to produce any kind of comprehensive picture of the field, and you will see that this indeed is far from that. So much more people than I will mention participated in development of the field, and I will be just following my subjective choices for open problems in homogeneous continua, and not only. So let's begin. So this is a discussion of open problems in homogeneous continua, and not only in homogeneous continua. And I thank very much organizers for doing this precious work, which is very important for our community. And I also thank you very much for this special invitation that I got. I really appreciate it. I know that this is hard work, and we need to continue that, and this is most important, probably most important event, annual event in our field. Well, I'm not talking about summer conference. Summer conference has different flavor. I would like to dedicate this talk to Janusz who was my PhD advisor. And he was a very exceptional person, great teacher, with great devotion to the work, and his determination in introducing people and helping them was well beyond what is normally expected as academic advisor. So I just wanted to give this sign of recognition of his contribution to, and his, thanks to him, I was really introduced in such a way that I cannot think of anything better. We had many discussions on various topics, including general ideas of mathematics, what is mathematics, what is motivation for studying mathematics, what is the nature of mathematical discovery. If we call it discovery, there is this dispute whether it is discovery or creativity. Also, I would like to add two more questions in the beginning before discussing mathematics that I think are relevant, perhaps not exactly to the topic of homogeneous continua, but to my study. I am taking advantage of this personal side of this presentation. What is the motivation for teaching mathematics? I was asking this question over and over and over, and my answer, so far the best, is that this is about awakening some deeper abstract aspect of mind. And this aspect of mind is essential in actually all academic disciplines and also beyond. This is the best answer I could have. Of course, there are other answers. So it leads to the next question. How did what I call reductionism in teaching mathematics get so dominant position? And throughout my work, I was asking this question over and over, but by reductionist, I mean reducing teaching of mathematics to computation, mechanical procedures, technicalities, and reducing motivation to applications. I think this is something that is very hurtful to our community, and I was asking myself all the time, why, how did it happen? How could it happen? So I leave this question. This is not mathematics. This is about mathematics. I think that this question may be relevant also to other people. Of course, I am not trying to impose my views of the matter, but at least as a challenge. So now about this talk, I have already mentioned this is personal, and I do not claim any kind of presenting any kind of comprehensive picture of the field. Field is active for over 100 years. Many people contributed, and I am just showing my preferences. Before discussing homogeneous continua, I would like to revisit fixed point result by Lee Moller from 1970s. It just happened that, well, yesterday, I think, Benjamin Wojna also was talking about it. So this is the result saying that each self-homeomorphism of a uniquely arcwise connected space, a continuum, has a fixed point property. And this result was actually well recognized for various reasons. One of them was using measure theory result, and as nice connection of continuum theory with other fields. And it just happened that during the last 2-3 months in Sacramento, we were having discussion about this problem and about this result. We were double-checking details. Several people were involved: Chuck Hagopian, Mark Marsh, Andras Domokos, and also there was some contribution from, as consultation from David Bellam. So I would like to recognize all these people. And in the process, I realized that this whole argument is based on another result that can be, and by the way, this result by Moller is based on a measure theory theorem attributed to Rogozin in the paper. So I will list two authors to this paper, to this result. Saying that there is, for every self-homeomorphism of a compact metric space, there is regular Borel measure on that space that is invariant with respect to that homeomorphism. So the whole argument can be stated also based on another statement which can be derived from this measure theory statement, namely that if we have compact metric space with one homeomorphism, self-homeomorphism of that space, and we think of orbits but not as sets of just points, but sequences, then it follows that the set of all sequential orbits with respect to that homeomorphism in the space does not admit an analytic selector. And what is new here that was observed, that this result can actually be quickly proved using purely topological methods, so quickly that I'm going to do it in this presentation. So the set of all sequential orbits of a self-homeomorphism of a compact metric space does not admit analytic selector. And here's this sketch of the proof. So we assume first that we are working with minimal closed set with respect to these homeomorphisms, intersection of potential selector would be still selector in this invariant subset. We consider the concept of quasi-interior of each of that selector. If it is analytic, then up to first category set, this analytic set is almost an open set. That means it may be missing some first category set, may have too much of but still by first category set. And then very simple set theoretic formula indicates that there must be some smaller invariant set, essentially smaller. So if we have iterations, we take iterations of these quasi. By the way, these quasi-interiors must be non-empty because otherwise it would violate Baire category theorem, and immediately we have smaller invariant set, and therefore the conclusion holds. So this was our surprise that it can be done so almost instantaneously, without much more elementary in the sense that we do. Well, we depend a little bit on descriptive set theory, studying these understanding these analytic sets, but no advanced theorem is needed. Basically, it is also based on Baire theorem. So this was just a curiosity. By the way, I would like to mention also that this non-existence of selector can be connected with, for instance, non-existence of analytic selector in some indecomposable continua, such as solenoids.
Is it possible to quickly define analytic selector?
It is an analytic set that intersects each orbit exactly at one entry. So if there is, for instance, a periodic orbit, it cannot happen because each entry in this sequence repeats itself infinitely many times. Yeah? So this is essential only when there is no periodic orbit. And selector is meant as a sequence indexed with integers. So, this is just curiosity. This argument can be used but to show, for instance, that some indecomposable continua do not have analytic selector for their composants. I right now don't recall the author, but I heard that there were results of this type, that there is no Borel selector. But this connection came to me just yesterday, so I didn't have time to search in the literature. So this is just a curiosity, and now we come to homogeneous spaces. The study began around 1920, attributed definition to Sierpiński. Space is homogeneous if for every 2 points there is a self-homeomorphism of the space moving one point to the other. Many important spaces are homogeneous. Euclidean spaces, the real line of those, rational, irrational numbers, the Cantor set, the pseudo-arc that has been mentioned in this conference a number of times, all manifolds connected without boundary, the Hilbert cube manifolds, the Menger curve manifolds, and topological groups, and many, many others. So this is certainly the topic that is close to, I don't know if in the center, but certainly has very special place in study in topology and beyond topology. So, yeah. Some definitions: continuum, non-empty compact metric space, classifying study of homogeneous compact metric spaces can be reduced to the study of homogeneous continua, because when we are within the class of homogeneous compact spaces, they happen to have product structure by Rogers result, product of a homogeneous continuum and a finite space or topological Cantor set. And this was the greatest adventure in my study. This is very personal. The pseudo-arc. I begin with the pseudo-arc, very special, continuum in the 1922, released by Knaster, who happened to be the advisor of Janusz Hanatonik, introduced first example of hereditary indecomposable continuum. His construction was in the plane. And in 1948, Moïse presented another construction, introduced the name of the pseudo-arc, and in his construction, all subcontinua of that continuum are homeomorphic to the whole space. Shortly afterwards, being showed that Moïse's example is homogeneous. I'm not going to precisely define that continuum. This is in the plane. We are having chains of links, and the next chain must be simply, well, simply speaking, but not simply doing, sufficiently folded within the previous one. How sufficiently? I'm not going into it right now, but being 2 years later, have proved a topological characterization of the pseudo-arc. For this characterization, we need the concept of decomposable continuum, which is the union of two proper subcontinua, otherwise it's indecomposable, hereditarily indecomposable, if every subcontinuum is indecomposable, chainable, if it allows epsilon maps onto or into, well, this is a discussion whether point is chainable or not, onto an arc, and tree-like if it admits epsilon maps onto a tree for every epsilon. So, in 1950, Bing presented a characterization of Moïse pseudo-arc as chainable, hereditarily indecomposable non-degenerate continuum. And this example shows this characterization. So that means that this is a unique space topologically up to homeomorphism. And this example showed that Knastet's construction, Moïse pseudo-arc are homeomorphic. Bing's characterization of the pseudo-arc leads to conclusion that in spaces such as manifolds of dimension 2 or more, Hilbert cube, and many other spaces, they dominate hyperspace of subcontinua in the sense of Baire category. They form dense G-delta subset. This, by the way, this property was also yesterday used by Sławek Solecki as very non-standard definition of the pseudo-arc. But this makes the pseudo-arc a very, very unique space. Among they dominate hyperspaces of all these big spaces of great importance. Another special property that I wanted to mention is that pseudo-arc has peculiar property. Whenever you have a sequence of pseudo-arcs in submetric space converging to a pseudo-arc in the sense of Hausdorff distance, that means this is set theoretical distance, not just set theoretical, it includes measure, but in terms of sets. Then they automatically must converge to that pseudo-arc homeomorphic. That means there are small homeomorphisms connecting the limit pseudo-arc with the terms of the sequence. This is very unusual. In fact, this is the only continuum that has this property. And there are very few spaces that have this property. Another one is
Right.
Also, finite sets have this property, and the Cantor set. And all compact spaces that have this property are just pseudo-arcs, product of the pseudo-arc, finitely many pseudo-arcs, and finite sets and the Cantor set. So it places the pseudo-arc among very special family of metric spaces. These and other extraordinary and amazing properties of the pseudo-arc open a door to unusual questions and wild speculations, at least in my mind. Again, I take advantage of this declaration that this is personal talk, so my question is it possible that the pseudo-arc represents some fundamental yet undiscovered patterns in mathematics and in topology, in mathematics beyond topology, beyond mathematics? And in fact, this question was on my mind for decades. In fact, when I came up with this question, when Luis showed me some paper from 1950s where Bing was asking similar question about probabilistic interpretation of the pseudo-arc, that the patterns of the pseudo-arc may perhaps represent a random walk, moving forward, backward, at say probability 1/2 moving forward, moving backward. And the iteration of this process. The problem, part of the problem is that there are obstacles to find some nice, unique measure space in which we would measure exactly what is the probability to obtain the pseudo-arc in the form of a random walk. And then it leads also to wild speculations. Again, I reveal perhaps things that are far-fetched, but I do not make any claim. I just simply imagine that some particle that seems to be an observation or stream of particles moving straight forward actually can be modeled by moving back and forth, back and forth, back and forth. And this model may capture something more, may be adequate and perhaps capture something more. I even managed to infect an analyst with this question and got excited, but again, it would have to be different type of thinking under different principles. It cannot be just taking the pseudo-arc and take existing theories in analysis or physics, for instance, or quantum mechanics, and you will have results. So some very different mindset would be needed for that. Again, these are wild speculations, so I am excused. I wanted to mention continuous pseudo-farms that I constructed years ago. A continuous pseudo-fan of this is a collection of pseudo-arcs, compact collection. This collection, each two of the collection have only one point in common. The collection, this point, common point, is called vertex. Any continuum connection between two members of that collection goes through the vertex. This structure has nothing to do with product structure, for instance. It is over specific space, compact space X. And when we take Hausdorff distances between these pseudo-arcs, then it creates, it recovers the space X. The collection is continuous. The whole continuum is one-dimensional, so it is embeddable in 3 space. And what I have proven is that for every compact metric space, there is such a continuous pseudo-fan or bouquet of pseudo. And with that, I have my visualization, because all of this sits in 3 space. My visualization is this. Let's have an eye whose focus is the vertex of pseudo-fan. These are actually pseudo-arcs. So I should draw something like this, perhaps. It sits in 3 space. If rays of light were going, say, along the pseudo-arc, along straight lines, this eye can only see objects of dimension 2. If there are 2 eyes and we have this vision as we have, we can also imagine 3 dimension. But with the pseudo-arcs, this eye can see the Hilbert cube and everything that sits in the Hilbert cube. And all separable metric spaces sit there. So this was quite impressive to me when I noticed that. Once again, in the structure of these spaces, the original space is embedded topologically. And they are almost disjoint except for the vertex. But we cannot find, for instance, a continuous selector here, because otherwise we would have Hilbert cube in 3 space. This was quite amazing to me. And so this is star-like continuum, these are tree-like continua, star-like continua, sitting in 3 space. They are all continuous images of the pseudo-arc. And I was have been having this question on my mind: what else can be expressed in terms of these pseudo-maps? Functions, inverse systems, geometry. Perhaps we can have strange geometry by properly putting the distances between these pseudo-arcs. Next topic: continuous and confluent images of arc-like continua. They were characterized as weakly chainable continua independently by Lelek and Fernley in early 1960s. They are called weakly chainable continua. Here we will just adopt definition. Weakly chainable continua are those that can be represented as images of the pseudo-arc under continuous maps. But there is structural definition for that. And these weakly chainable continua have, I consider it very regular class, even though it is much similar to locally connected, even though it is much less intuitive. There's no local characterization, for instance, by small neighborhoods. Fermi has also shown that weakly chainable continua are closed with respect to finite unions and countable products. This is part of this regularity of the class. So continuous maps from the so we can because of this Fermi property, images of the pseudo-arc form what I call pseudo-paths of every space. Decompose the space into mutually disjoint pseudo-path components, just like we have path components of every metric space. A map between two continua is called confluent if for every subcontinuum in the range and every component of the pre-image, the image of that component is the whole continuum X, continuum K. Weakly chainable hereditarily decomposable. They happen to be homogeneous tree-like continua are known to be exactly the same as homogeneous hereditarily and decomposable continua. So the one direction was proven by myself and Krupski, the other one by Jim Rogers. And Jim Rogers was first, by the way. I'm just writing first the forward expression. So recently we have had major breakthrough in the study of homogeneous continua, namely classification of complete classification of homogeneous continua in the plane, the pseudo-arc, the circle of pseudo-arc, the circle of course, by Hahn and Oversteven. And I think that in the pursuit of the study of homogeneous continua, hereditarily indecomposable or and weakly chainable, or equivalently, weakly chainable and tree-like is the next beast to hunt. And that this is right now somehow accessible. So I expect, and I'm also focusing on this topic, so this is also a challenge to others. This is the next thing I think that should fall. And this problem was around, has been around for many decades. So the question originated was formulated by Andrew Relic. Is every confluent image of this is more general question. Is every confluent image of an arc-like continuum an arc-like continuum? And it is also related to question by Cook and Lelek, do confluent maps preserve on continua preserve span zero? In view of an overstricken result, this would be sufficient actually for knowing that tree-like weakly chainable continua are pseudo-arcs. And it is also related to the question by Ingram, does there exist a homogeneous tree-like continuum of positive span? So if answer is no for this question, we would have characterization of all tree-like homogeneous continua as the pseudo-arc only. So this is history, but history that is very relevant at this time, I think. Weakly chainable homogeneous continua. Each pseudo-path connected homogeneous continuum is weakly chainable. That means if we can connect in a continuum every 2 points with a weakly chainable continuum, then the whole thing is weakly chainable. It's very different behavior from path components. There are path connected, non-locally connected continua. Locally connected is equivalent to being, by Hahn-Mazurkiewicz theorem, to being a continuous image of an arc. But for the pseudo-arcs, it behaves much nicer. It means if we can connect every 2 points of a homogeneous continuum with an image of the pseudo-arc, the whole thing is an image of the pseudo-arc, and this does not hold beyond homogeneous continua. It means there are pseudo-path connected non-homogeneous continua that are not weakly chainable. A subcontinuum of a continuum is ample if every neighborhood of that continuum contains another continuum containing the original one and its interior. So we can enlarge it slightly to something that has the previous continuum in the interior. And there were somehow in recent study, I realized, and not only myself, David also noticed significance in the work with Janusz, right? Significance of the diagonal of the product. It turns out, and at first it was proven by David and Janusz, that the product of 2 pseudo-arcs or finitely many pseudo-arcs have ample diagonal. It turns out that it can be generalized to all weakly chainable homogeneous continua. For weakly chainable homogeneous continua, the diagonal is always ample. Question, does the converse hold? Does the converse hold? If the homogeneous continuum has a weakly ample diagonal, does it follow that, that the continuum is weakly chainable? By the way, the answer is yes among topological, compact connected topological groups, among isometrically homogeneous continua. These are some of my recent results. So I would like to expand it to the class of homogeneous continua. Hereditary weakly chainable. So this is another natural class, not very much explored actually. The name is long, but it captures something very natural. Perhaps somebody will come up with a more concise name. I think it's worth. A continuum is hereditary weakly chainable if every subcontinuum of that continuum, not only the whole continuum, but also every subcontinuum is a continuous image of the pseudo-arc. And again, in view of the recent breakthrough by Lex Overstiegen and maybe alphabetically Logan and Lex Overstiegen, the following question comes to my mind, and I think it's relevant. Is every non-trivial hereditary weakly chainable homogeneous continuum a circle, the pseudo-arc, or the circle of pseudo-arcs? In other words, is it the case that a homogeneous continuum is hereditarily weakly chainable if and only if it is embeddable in the plane? And I think that, again, we have enough tools to start biting through things like this. It'll be most interesting. Hereditarily non-weakly chainable. Now let's examine the other. In mathematics, we sometimes are particularly interested in opposite edges of the spectrum. Recently, Janusz presented result that the product of any two planar continua contain hereditarily non-weakly chainable continuum. No subcontinuum is a continuous image of the pseudo-arc except singletons of the pseudo-arc. So I have conjectured actually that every continuum of dimension 2 must contain hereditarily non-weakly chainable continuum. It would be quite similar to hereditarily indecomposable continua and early result by Mazurkiewicz that says in dimension at least 2 there must be hereditarily indecomposable continuum. And my question is, does there exist a non-trivial hereditarily non-weakly chainable homogeneous continuum? Once again, these are natural classes, even though the names are long and sound artificial. So, next topic, special cases for previous questions. Yes, this is non-trivial. Yeah. So does there exist a homogeneous continuum that is hereditarily non-weakly chainable? This would be something very strange out of the patterns we developed so far. A question by Krasnikiewicz means revisit. The following question has been a major challenge. Let X be a non-trivial, hereditarily decomposable homogeneous continuum. Must X be a simple closed curve? I consider special case because the question is open for decades. Can we solve this question at least among hereditarily weakly chainable continua? I cannot. Does there exist a non-trivial, hereditarily decomposable, hereditarily non-weakly homogeneous, non-weakly chainable homogeneous continua? So these are again these two extremes. Let's consider Krasnikiewicz and Means question among hereditarily non-weakly chainable continua and among hereditarily weakly chainable. Maybe somebody can come up with a quick answer to one of those. Because these are strong extra properties. Intrinsic decompositions of homogeneous spaces. The partition D of a compact space into closed subsets is called intrinsic or topological decomposition, provided for every self-homeomorphism of the space, the image of the fiber or member of the decomposition is in this decomposition. It means that this decomposition is inscribed in topological structure of the space. It's not like the composition of the plane into lines where we can have many ways of doing it. It is uniquely determined by topological structure of the space. And such decompositions are known, for instance, most obvious interconnected components. And this decomposition represents a duality between, the decomposition into connected component duality between connected versus totally disconnected. In a compact homogeneous space, this is reduced to the product by Rogers result as mentioned before. Other, less obvious intrinsic decompositions of homogeneous compacta have been extensively studied. They provide important structural information of a continuum. So these decompositions are always continuous. Members of the decomposition are homogeneous. The quotient space is homogeneous. And these decompositions not only are homogeneous, but also nearby fibers can be moved by small homeomorphism. So some of the best possible way we can decompose the space. The decomposition into connected components represents duality between connected and totally disconnected. For other intrinsic decompositions that are known and studied and have been studied are aposynthetic decomposition by Jones, mutually aposynthetic decomposition recently added by myself, the terminal decomposition defined by Rogers, and the semi-terminal decomposition also recently added by myself. So we have aposynthetic decomposition. We need the definition. The continuum is aposynthetic between 2 points. If one of these points can be embedded, sits in a continuum in the interior of some continuum that misses the other. Terminal, if any subcontinuum intersecting that continuum either contains or is contained in that terminal continuum. So these phenomena can be observed in simple example like topological sine over X curve. But finding this phenomena among homogeneous continua is far from, had been far from obvious. Nevertheless, such examples exist, such as the circle of pseudo-arcs, which was the first actual example of earlier defined by Jones, the aposynthetic decomposition. The aposynthetic decomposition represents duality between indecomposable and aposynthetic. The quotient space is aposynthetic, the members of the decomposition are indecomposable. The terminal decomposition represents duality between terminal, maximal proper terminal subcontinuum, and quotient without any proper non-degenerate terminal subcontinuum. In many examples, the terminal and aposynthetic decompositions are the same. Solenoids of pseudo-arcs are examples where they are different, so they are not the same. The mutual aposynthesis was introduced by Chuck Hagopian. It is similar to T2 axiom in general topology. The space is mutually aposynthetic between 2 points, and we have disjoint continua having one of the points in their interior. It can be also defined using amplitude. The product of 2 pseudo-arcs and the product of 2 solenoids are examples of semi-decomposable aposynthetic continuum. The mutually aposynthetic decomposition was added around 2007. There is such a decomposition. It represents duality between mutual aposynthesis and semi-indecomposability. There are many examples. My question is, in many cases I could prove that the members of the decomposition are connected and they are actually semi-decomposable, but I still don't have general proof. And this would be important addition to this mutually aposynthetic decomposition theorem. So I see the time goes very fast. I want to get to some places. Is every homogeneous indecomposable continuum one-dimensional? Old question by Jack Rogers, right? So we suspect that indecomposability among homogeneous continua is strictly related to dimension 1. Similarly, we have similar questions about semi-decomposability and semi-terminality. Is this non-mutual aposynthesis or semi-indecomposability but aposynthesis strictly related to dimension 2? I offered 3 questions. Is every homogeneous decomposable, semi-decomposable continuum exactly two-dimensional? Is every homogeneous one-dimensional, semi-decomposable continuum indecomposable? Is every homogeneous one-dimensional aposynthetic continuum mutually aposynthetic? These 3 questions are interconnected and they point exactly at the same place, that this non-mutual aposynthesis among homogeneous continua is somehow related with dimension at most 2. Maybe I will skip this one. Can I skip this one? Because I want to get to, yeah, I will skip this one. I will skip this one. Homogeneous continua in 3 space. This I wanted to include. Because I think it's also time that we should be capable to classify locally connected homogeneous continua in 3 space. Are they a circle, the Menger curve, an orientable 2-manifold, or a Pontryagin sphere, which is related, and in fact the second question would solve the first one if in positive, if answered in positive. Is the Pontryagin sphere the only two-dimensional locally connected homogeneous continuum in 3 space that contains no disk? And last page. I'm sorry for going fast, but I don't want to extend this talk. Yeah. Once again, is the Pontryagin sphere the only two-dimensional, locally connected homogeneous continuum in 3 space that contains no disk? If yes, then the first question has positive answer. And it would be a complete classification of locally connected continua in 3 space, certainly desired. We want to know what are they. And last page. Oh no, second last. Isometrically homogeneous continuum is a continuum that admits compatible metric in which it is homogeneous with respect to isometries. And these continua fall into 3 classes: indecomposable, aposynthetic and semi-indecomposable, and mutually aposynthetic. This includes compact connected topological groups, which was not known actually before. And here are my questions. Here is my last question. Let X be a non-trivial isometrically homogeneous continuum in 3 space. Must X be homeomorphic to one of the following spaces: a circle, a solenoid, 2 sphere, or 2 torus? Certainly something that we would like to know. I would like to know, definitely. Thank you for your attention.
Are there any questions or comments?
What is the boundary
Jagan's sphere. I don't.
I wanted to say something about it. I apologize for speeding up my speech. I probably would to add some details, background, discussion, and so on. It would have to be different presentation. But this is not original definition. The definition I tend to think with is starting with the Sierpiński carpet. And so on. So this is infinite construction that probably everybody in this room has seen. And apply in this window, including the outer window, I consider outside also window, standard identification that produces torus. That means this side with this side, this side with this side, but do the same with every window. So it produces something that I sometimes call sphere with null sequence, dense null sequence, infinite sequence, dense of handles. Null sequence, that means these holes become smaller and smaller. Beautiful space to visualize. Happens to be, well, local connected, obviously, but also homogeneous. And it sits in free space and contains no disk. So do the same with every of these windows. This is a nice, simple, elegant way of thinking of which I can see, at least to my taste.
Go ahead. Has anything been written on the suggestion of Bing connecting the pseudo with other words?
It was, I am not aware of, except his original question. I found it afterwards, after thinking of this, in some collected papers by Bing, around 1950.
This may be a joke, but I have a friend who started life as an engineer and then went into marketing, but has been studying organizational behavior in large organizations. And I gave him an encapsulated description of the pseudo-arc once upon a time, and within a week he had decided the pseudo-arc was the perfect model of the decision-making pattern within chains of command where nobody wants to take responsibility for the decision.
I can talk another 20 minutes about associations I have with the pseudo-arc. One of which is any kind of growth, and true growth goes like this, going forward, going backward, forward, backward, until we examine the path so well that we can make progress. All kind of things can be modeled like this, yes. I 100% agree.
Another question or comment? Well, let's continue that during the dinner. So.